Today's going to be a really quick and easy day. This is called the free body diagram. Now, what is a free body diagram? A free body diagram, or FBD is usually commonly shown, is a pictorial representation of all the forces acting on the object. So what do? We use arrows to represent forces, and their direction indicate the direction of the force, and then how large the arrow indicates their magnitude. So a bigger arrow represents a bigger force. So a magnitude is expressed by a number or the arrow size. The forces are measured in units called pounds or newtons. Notice that pounds is not a mass unit. Okay, it is actually a force unit. So, common forces. There is weight or gravitational force. That's always downwards to the center of gravity. We always label it F sub g, force of gravity. There's an applied force. This is any push or pull by a thing or an object, symbolized by F sub app. There's normal force. And this is the force from a surface on the object, and it is always perpendicular to the surface, F sub n. Now, this is important. Normal force is always perpendicular to the surface, never straight up. So if you have a surface that's at a slant, let's say a hill, it's going to go perpendicular to the surface. So that's going to go up and away, not necessarily straight up. Normal force never counteracts gravity 100%. It can if it's on a flat surface. If you're leaning against a wall, then the surface is coming out at you. The normal force is actually coming towards you from the wall, keeping you from falling into the wall. There's friction. This is always exerts when there's motion across a surface, and F sub F. And this is always going to the opposite direction of the motion. Air resistance is a special type of frictional force when acting upon when objects travel through the air, and again will be acting in the opposite direction of the air resistance. That you can usually see that as F sub air. We won't deal with air resistance too much. Tension force is how tight ropes or cables are, F sub T. And spring forces are when you have springs, F sub S. Now, when you sum up the forces, we are going to add up all the forces, and they have to be equal to 0 if there is no acceleration. If they do equal some number, then it's called unbalanced forces. So we have balanced forces and unbalanced forces. If all forces are balanced, that means all my ups forces, which is in the y direction, equal my down forces in the x direction. This will have a they will either not move or have a constant velocity. We call this situation static. Now, if it's unbalanced forces, then you're going to have forces where you can accelerate, speed up, or slow down. We call this dynamics, because the word dynamic meaning motion. We will deal with dynamic systems later on. So here is a situation of a free body diagrams. I have an object, and I just drew a square because it was easy to do. And it doesn't matter, it can be a dot or a square. We always simplify the drawing. We don't need to draw out the whole thing. And then I have my force up, it has to equal my force down. My force left has to equal my force right. So my friction has to equal my applied force, and my normal force has to equal my gravitational force. Here's another example. I have normal force pushing up at 20 pounds and gravity pulling down at 20 pounds. Unbalanced forces are like this, where you have an applied force, like a car engine, is way higher than the frictional force of, let's say, the tires on your car, and you are speeding up. In this case, this would also be falling down and going forward, so this would be like an airplane doing a maneuver diving down and to the right. So how do you draw a free body diagram? Well, first, you sketch what's happening. Second, determine the forces that are acting on that object. Then third, you draw the object in isolation with all the forces acting on it. So let's go an example. A college student rests his backpack upon their shoulder. The pack is suspended motionless by one strap from her shoulder. So let's see. So I sketch out what is happening. Now I have to figure out what forces are acting. Well, I have gravity pulling the backpack down, but I also have that strap, which is tension force, pulling the backpack up. So then I draw a simple thing. I isolate just the backpack. I'm looking at the backpack alone. I don't care about her. I don't even care if it's a her. It could be, a hook. It could be hanging on the backs of a chair. But it would be identical in situation because the backpack is still being pulled down by gravity and the tension being pulled up. Now, I want you to practice this and practice these on your notebook. An apple is sitting on some books on a table. What would the free body diagram look like? A man pulling a box to the right. He isn't pulling hard enough to overcome friction. So pause the video and do that. All right, you should have just paused it. If you haven't, please do so. Okay, so here it is. I have my apple. Again, I'm just drawing a dot. It's really easy. I have gravity because everything's being pulled down by gravity, and it's sitting on a table, so there's normal force pushing up. It's what's keeping the normal force is what's keeping gravity from pulling the apple down through the table. Is the normal force or the force of the table pushing up. Now, a man pulling a box to the right, we know that he isn't pulling hard enough to overcome friction, so it's stationary. So it means the arrows have to equal the left and right. So gravity's still pulling the box down. The floor is pushing up equal with its normal force. They're applying a force, and we have a friction to the left, and it has to equal the same size as my applied, and because it's not hard enough to overcome friction. So if you have any questions, you can write them down, ask me, and we will deal with some more of these free body diagrams come here shortly.